So I guess it's good to continue our journey on game theory, which is the topic that I more used to because I do it for my living. So I just do research on this game theory. Although I'm not a game theorist, but I'm applied game theorist. So basically, I use mainly use the theory rather than inventing a new theory. So I apply this to different contexts like IO or political economy. So just very brief review of game theory. Okay, we just focus on these four main areas that cover in standard game theory textbook. I mean, of course, as I mentioned last class, there are things that related to the cooperative game theory which we don't cover. The idea of cooperative game theory is like the core we talk about in general equilibrium. Okay, there are a lot. I mean, nucleus and bargaining set, and these actually, I mean, some of you asked me the contract design, mechanism design in decentralized contract or smart contract, or those concepts actually can be useful when you design things. You want to achieve an outcome, and what a good outcome, then those actually is very helpful. So you want to check that as well. Actually, these concepts are heavily used in computer science and others, because you will see Nash equilibrium, and there are many in some of the games. There's some games they don't have Nash equilibrium, but there are games that have many Nash equilibrium. So which one to pick, which one to choose? Sometimes the cooperative game theory can tell, right? You want to choose the one in the core, right? Core is or individual rational or Pareto efficient. These are how to rank outcome, how to assess different outcome. Then it's very important. Okay, but we'll focus on the first case in this, and there are many textbook here. As I mentioned, I recommend this textbook if you have time. Okay, so I'm not going to talk about from how can we from monopoly to perfect competition, but just to remind you that the monopoly problem is the firm choose quantity or price. I mean, either one of them, right? Your downward sloping demand, and here is the firm can just decide what they want, right? Everything is exogenous to him or her, so that means that is a decision problem. And the perfect competition is other extreme is also a decision problem. The reason is being that although the demand function or inverse demand function is also with your QI is also inside, okay, but the perfect competition means that you don't think your action affect the price. Okay, is it whether your action affect the price? It doesn't really matter. Just they think that they don't affect the price. Okay, they act as if the price taker. Okay, just like people from finance, right? They would argue that you send the order to the market, actually the price would adjust, right? But if they think they will not change it, okay, and then this will be the outcome. Okay, and of course this outcome is justified if everyone is small, right? If small, then your order doesn't change the market, or maybe a little bit, right? In that case, this is a good approximation. Okay. So although here we often just say, okay, this is very simple, but in this very powerful. Okay, perfect competition is a very powerful concept if you are to apply in your practice. Okay, indeed, you may be surprised to notice, say, central bankers or a lot of consultant firms, a lot of things outside in the practice, they happen to use very simple model, like demand and supply, actually can carry very far. Okay, of course, there are some assumptions behind those analysis. We study those, and then you have to know when you use them, what the limitation. But indeed, in the real world, they use that, right? I mean, just very simple. Look at the M.B.A. people. Look at M.B.A. what they teach, right? They don't teach this kind of stuff, right? They just teach very simple demand supply, right? When you go to them, they do those light things, those simple model. And actually, those executive on top people are thinking this way, right? So that is not that is still very. But of course, for many of you actually doing academic research, that would not be sufficient, right? But in terms of, if we talk about macro, that would be perfect competition would be a good one. It's a good approximation. But although these days they talk about market power, you look at papers in international trade or more paper in macro, they talk about those market power. But perfect competition already capture a lot of things. Okay, so although we talk about game theory, which we use on research, but for us, if you understand the world, perfect competition, I mean, we learned in last class. If you learn how to do appropriate demand supply analysis, then actually you're very good. But anyway, this is a PhD class, so I don't want to side check a little bit. So just to remind you that what's game theory, right? It's just a good name. It's just a interactive decision theory, right? Just is a multiple agent in the model, and each one is making decision, right? And say duopoly, right? There's the inverse demand curve depend on the output of two guys, right? So how much you produce depend on how other people is producing, right? So the question lies on what would be the prediction of this kind of model, right? It's because depend on each agent's choice is depend on the others, right? What is your prediction, okay? And in our class, we only focus on the case what we call equilibrium. Okay, we focus on the prediction such that it's called satisfy some called stable condition. Okay, and in different type of game, you have different stability condition. Okay, and of course, you look at game theory textbook, there's something more than stability idea. Okay, because sometimes we observe in the world that not just equilibrium is observed, and sometimes you don't have equilibrium exist. So that's why I look at the game theory textbook, they have a much more less because equilibrium actually require much more demanding assumption, so they have a relaxed definition of stability here. But we focus on the equilibrium idea. Okay, so what is the say for example, what is the requirement besides stability? So is the idea looks like what we learned, the dominance, right? I think before we go, there's 4 different concepts that actually use in practice. Okay, and this is actually you found in the most of application they use this. Okay, or there's some further refinement, but this is usually the basic thing you can find in most of the papers. Okay, so so first thing we have to define the game first. Okay, how to define the game, and it's always start with 3 elements: player set, strategy set, and payoff function. Okay, so the player set just define who are actually players. So it's very important because of our interactive decision theory. We have to be very clear who are the players. And how do you define the strategy? And how you define the payoff function? And it is very important. You have to make sure that every agent, you have to make it very clear what are the payoffs. Okay, and the reason why you have to be very careful, and in fact, you should also be careful to talk about people who is also exogenous in the model. Okay, and recent example, actually, I work with another co-author who is also working on some problem, and we consider a firm and their customer, and some customer are locked into some of the firms, so they have to purchase. Actually, we see such a model later. But if you are not careful, because this guy are locked into one firm, though they must buy that firm. So if you don't actually model their payoff, okay, then you end up in the case that the firm can charge very high price, right? Because they're locked in, they can charge as high as they want, right? So you have to be very careful. In that case, you have to actually, even though they are not players, you have to be very careful how to model them. Otherwise, you can say the firm, the choice is unbounded, you can charge as high as possible. So I mean, my co-author didn't notice actually this is a problem, right? So I mean, here I focus on the case where the player, you have defined the payoff, but you have to be careful for those agents who is not strategic, okay? and you have to be very careful in those, say, in finance model, you have to say some players who are a uninformed trader, right, or random trader, and then those people, I mean, you still have to consider what are the payoff, right? Although they're stupid, right? They're automatic. You make sure that your automatic thing makes sense, right? Otherwise, you can say the broker charge infinite brokerage fee, they will still come no, right? They will have some limit to upper bound that they will still remain in the system. Okay, so we have to be very careful. Even though I put a game here, you have to make sure that everything would make sense. Okay, even though you didn't allow those people, right? Just like the demand, just like look at this problem, right? The monopoly or duopoly, right? Here you actually the firm interact with consumer, right? But your price is actually a reduced form, or we call it, it's a version that how consumer choosing their quantity given the price, or given the quantity how much they're buying, right? So that means that this is actually, you have to be careful, you make this assumption, right? What is it behind, right? In a simple model, you don't realize there's a problem, but when you add a lot of things there, you just try to make sure that these will make sense. Otherwise, I mean, you don't notice because the model is vastly complicated. When you have many stages, many things, then just be careful, okay? Because that is just my recent experience. So you have to define the three things carefully. So player set is usually very simple, just there's nothing usually, but and you have to make clear who is doing strategic choice. Okay, here is like here say firm competing, right? So consumer are at the background, don't make any strategic things. Okay, so you have to be very careful. And the next is about strategy set, right? So you have to also be very careful about what the firm can choose, and particular a technical complication later you will see as well is say if it's continuous, is it an open set and closed set? Okay, and boundary is important. And as matter of math, you also usually want a closed interval while an open, because open interval usually you might not have solution. Okay, that's a mathematical result. Okay, so that's why usually you would want to restrict like this. Usually is not a very good idea because equilibrium existence will be an issue. But for production, it's okay to do this. The reason later actually we'll argue is because of the demand function is downward sloping, right? There's a maximum quantity actually you can produce for the price to be meaningful, right? Because usually this is P, this is Q, right? And then I don't know where you start, but anyway, how you go down, but at the end, usually the Q star or Q max, such that P of the Q star will be 0, right? In that case, no one will produce way more than that, right? Because beyond that, there will be 0, right? So that actually it's a bounded one, right? It's a closed set, right? It's okay to restrict your idea that this is the strategy set. Okay, and actually this is obviously as long as your cost is positive, right? This is certainly dominated, so you can eliminate it, right? So we'll talk about set dominance afterward, but that is usually how you can argue your strategy set is within a bounded one. Okay, and just idea that every agent, every firm can have a asymmetric strategy set. Don't have to be symmetric. Okay. But do not later you will see a strategy set can be asymmetric, but you can still have symmetric strategy. Okay? Later you will see what do I mean by that. Anyway, this is payoff function. Okay, payoff function is defined as look at the strategy profile, which is vector of strategy, is a mapping from this set of strategy to a number, right? Just basically, if all the people choose this strategy, this is the payoff. Okay, and at the moment, the payoff here are ordinal only. Okay, we just require things are ordinal. Okay, because we're focusing on what we call pure strategy, which we'll talk about mixed strategy soon. But here everything is ordinal. Okay, just to remind you, This is the three thing. Okay, you have to specify player set, strategist, and payoff function. And in business journal, usually they don't define this a formal way. So they will just, you can see the description, to firm, firm, and firm, to what they do, and what's the payoff. Okay, but when you look at the econ journal, they will just define like this way. Okay, or computer science, you will see they define this way. Okay, so either way is fine. Just make sure that, I mean, when you write your term paper, if you want to write game theory, then if we are in econ class, so try to do that. I mean, of course, you have to explain this as well. Okay, because in business application, I mean, math is not important, but just a tool, right? So just make sure that if you write the math, make sure you also write the English properly. Okay. So you should be, I mean, here I'm not very careful. Maybe I should write P is the inverse demand function, and this is the cost function. I mean, I have to write that down, but I'm just lazy. Okay, not a good example here. So dominance for strategic form game. So that will be, we call dominance. And this is the first, also the easiest way to handle is if a strategy is always stupid, okay, for all other people strategy, this is always worse than this one, and there's no reason you choose this over this guy, right? So this dominated, this dominated this one. Okay, this is being dominated by this guy, this dominates this. Okay, and if this is stupid, then you expect someone with is rational, then you should never choose S, right? So the next is if the game is such that everyone have one strategy that dominate all other strategy, then that one is a prediction, right? So just recall the most famous game, Personal Dilemma, right? Just to remind you that D is the dominant solvable. May just repeat because I think it's important. So look at this matrix, right? This matrix actually tells you, sometimes they call the by matrix, payoff by matrix. So you can see the player set, strategy set, payoff function, right? So this is the payoff for -1, right? CC, right? This is payoff for guy number 1, this number 2, right? So look at the case, focus on we are player 1, okay? If player 2 choose C, I would choose D is better than C. If player 2 choose D is better than C. So D dominates C, okay? And same for the other guy because it's symmetric. So D is a only reasonable choice, regardless of how you would do, right? D is being chosen, right? And you can easily see that that is the only thing you can predict, right? And sometimes and usually you can't find you cannot have this nice outcome. So one of the other way around is you repeat applying strict dominance more than once. You keep doing it, right? Because once you do it, you make the game simple, right? Because once you take out one strategy, you have a new game, right? So basically, you keep reduce the game into smaller and smaller one until you get the end. Okay, and like this example, right? So initially, you can't really find which one have a dominated strategy, but for 1, right? But if you look at 2, you can actually eliminate R, right? Because compare R, C and R, right? Under U, C is better than R. Under D, C is also better than R. So R is gone. So basically, you become a 2x3 game, become 2x2 game. Once you become 2x2 game, then U is better than D, right? Then you get remove this guy, right? And in this case, you can see C is better than L, so you just left this guy, right? So just keep doing this, and of course, Is it easy to see UC is the only outcome? It's not that clear, right? Although if they're smart, if they play this game long enough, yes, right? Usually in lab experiment, if you allow them to learn, if they keep playing this game, at the end they will figure this out. Okay, usually, okay, if it's not too complicated. But in the real world, a lot of time we don't repeat many times, and then we don't interact long enough to know this is the right thing. So actually, in the real world, they are more complicated than this. Okay, but that is being if you do experiment, right? Behavior. If you are a normal game theory person like me, then I just take this. I would say just say UC and that's it. I will not go anything further. Okay. Also, you can check. This is the only Nash equilibrium. Later, we'll define the Nash equilibrium. Right? You look at this. 1, 2 is you don't want to deviate, and then this is also you don't want to deviate as well. But we'll talk about Nash equilibrium later. But that would be the outcome. Okay. And in this case, actually, you don't. It's not going to solvable by this. There's nothing dominated, and actually, you would be expecting the best outcome for 2 of them, 6, 6, should be the outcome from this game, right? You expect this as a rational prediction, and indeed, you talk about Nash equilibrium, yes, okay. But we'll talk about this now. Okay, so the Nash equilibrium. So Nash equilibrium, just to make sure you understand, is although it's very simple concept. Okay, the definition by itself is very simple, but you have to make sure that you understand 100% of it. Okay, it's very important when you learn game theory. Most of definitions are very simple. Okay, but you have to make sure that you understand perfectly 100%. Otherwise, you would apply it wrongly. Okay, so make sure that you check every single word very carefully. Okay, so here we will say this is very simple, right? The Nash equilibrium just saying that, okay, a profile, which is the list of, look at this outcome, okay, this is a profile, and you just try to change player I's strategy, okay, and there's no way you can improve it strictly, that remain the same, okay, then this is the Nash equilibrium, okay. You need to check for every single player, no one can change their action or strategy such that his payoff is strictly better. Okay, there's no other. In that case, then it's called Nash equilibrium. Okay, so that is very simple. Okay, just make sure you understand. Okay, and we'll see the example. I just changed a few slides here. So these are properties that are Nash equilibrium, and the first one is unfortunate fact is in some cases they will not exist. Okay, we'll talk about existence at the end of this topic. Okay, and the next one is we call multiple Nash equilibrium. Also a problematic thing, right? When you have no equilibrium, so what's the prediction? Okay, that is a problem. Okay, and in that actually will be a main research topic actually for game theories. Okay, with a more simpler construction. But in application, okay, if a game that has no Nash equilibrium, then either we focus on what we call the mixed strategy. Okay, usually then the model will be a lot more complicated. Okay, and that is usually the way you solve the problem. Or you would be change the game. Okay, there's 2 ways to do it. Either you change the game or you make mixed strategy. Okay, and mixed strategy, I would argue, in some case it will make sense. In some case they do not. Okay, so and that's why I would rather change the game. Okay, so that is a tip step from me. Okay, so the next one is you have more than one Nash equilibrium, and that is sometimes often happen in practice, and you probably want to see which one is better. Okay, and that is very often that you have multiple Nash equilibrium, and which one you would like to see. Okay, you have to argue one is more reasonable than the others. Okay, there are many criteria we'll talk about at the end of this topic, and that is actually very important to analyze. Okay, and then obviously Nash equilibrium usually doesn't mean Pareto efficient. Okay, actually we see that from the personal dynamic, right? But anyway, that actually, as I mentioned, is kind of a reason why first welfare theorem, okay, fails in general case, right? First welfare theorem holds when we have market and we're perfect competition, right? But when we assume price taker, right? When we just relax the idea of price taker, okay, then first welfare theorem fails. And that's why I explain why we have market failure. Of course, that's why also we have government failure as well, but that would be the concern. Okay. So I just put this slide earlier because I want to emphasize it's easy to have no Nash equilibrium. Okay? And here I introduce a term we call zero-sum game. Zero-sum game means the payoff, sum of the payoff is zero. Okay. So which means that my gain is your loss, my loss is your gain. Okay. So which means that there's nothing new. I just move it to the from the back because you can see this is the what we call the simplified rock paper scissors. Okay. So basically it's a two guy. Okay. Here's a coin in the pocket. Okay. And simultaneously they take out the coin. Okay. And if the coin are different, okay, if the coin are different, player one win $1. If the coin the same, player one lose $1. Okay, so just repeat this. Player one and player two put out the coin together. If they're different, player one grab the coin. Okay, if they're the same, player one give player two the coin. Okay, there are many coins in their pocket. Okay, this is a game. So it's a simplified version of, we're going to say, the one-dimensional rock paper scissors. Okay, and you can easily check that none of the strategy is going to be Nash equilibrium. Why? Head, you want to, for player one want to go to tail, right? And if here, player two want to go to here, right? It's a cycle. Okay, there's no Nash equilibrium in this one. Okay, so and you can see the what with a prediction here, right? And that actually go to the idea when we learn when you are in the kindergarten, how you play rock, paper, scissors. Always rock, okay? Always scissors, right? Always paper, or the trick. This means everything, right? No one knows, right? This is a rock is here, scissors is here, paper is here. So we just represent everything, but let's say fail. I mean, you only allow one of the three, right? So usually we just what we call randomize, right? You don't let the other people know what you're doing. And later we will try to argue, what do you mean by you don't let other people know what you're doing? Okay, that is called mixed strategy. Okay, and so the answer to this is we are just, because there's no Nash equilibrium, we try to allow that player try to randomize over these two. Okay? Then that means that the strategy is a compact set, so you have some kind of solution. But anyway, so the other I also add is what we call the pure coordination game. Okay, because this is also have the result here. Okay, here the game we call stat hunt game or coordination game is saying that the two villagers try to decide whether to hunt a stag or hare. Okay, and if they all go for the hare, they got 5 payoff. Okay, they were pretty successful. Okay, if they actually go to stag, which is a very big animal, okay, then they are going to kill it, they get 10 payoff, right? If they diverge, right, hare is very small, right? So then it's very successful for the girl, right? The boy is not going to success, right? Same here, right? The stat, then same here, 8, right? So what would be the Nash equilibrium here? Actually, you can see the these two corners are the Nash equilibrium, because here 10 you don't want to deviate, this you don't want to deviate, right? Do note that you don't compare these two directly, right? For the Nash equilibrium, is only compare individual deviation, right? So we just compare for any outcome, you compare the column and you compare diagonal. Sorry, compare column and row. You don't compare diagonal. Is that clear? Because you just compare single deviation, right? For 5 and 5, you don't need to worry about compare these two. Right? Just compare up. You compare up for the first coordinate, right? Compare column for the second coordinate. Okay, row for the first coordinate, column for the second coordinate. Right? So that is a simple comparison, and you can see that this equilibrium dominates this one. Okay, so you can see this is the result, and you can see that two Nash equilibrium, one is better than the other. So what we expect to be, okay, and all of us probably want this one, right? But this one also possible, right? Actually, this is related to the idea what we call the sunspot equilibrium in macro, right? It can end up, yes. Okay. Yeah, okay. I said this Pareto dominate this means that payoff of everyone here is better than payoff of everyone there. So we say outcome X Pareto dominate Y means UIX is, the strategy profile, okay, is better than UIY for all I, and this is strict for some I. Okay, it's not the strategy dominate. It's not about the outcome. Outcome and our Pareto dominates. It's like the Pareto dominance, right? The same as what we learned general equilibrium. But very good question. Okay, so means this is better for every. Okay, you don't like dominance. Say this outcome is better for everyone compared to this one. Okay, and in macro they talk about this is the boom, this is recession, right? Boom and bust, right? It's a good economy, bad economy. Okay, and why we have this? Well, that is because people coordinate, people are happy and they invest and they're here, and people are depressed is here, right? The financial market also people talk about, right? Whether the bubble is here, then no bubble is there, right? So on and so forth, right? There are many versions, and also political economy like this one very well, okay? And they would argue that how you get here, okay? That here is actually the rank of being a ruler, the rank of politician or the leader, so-called, right, in the village tells us, okay, today we're going to do this, okay, and he can get the rank of coordinating people. That is the rise of political power. It simply comes from coordination, because people cannot coordinate. Okay, you need someone to organize them, right? And that has been a case in the history, right? They said Chinese are bunch of loose ends, 一盘散沙, and then you need some strong men to handle them, right? That is the idea, right? Until the institution or the rule or custom have been formed, to do this, you need that thing, right? So anyway, if you look at the history, whatever history, in the human history, not just restrict to China, is like this. Right? That is not invented by me. It's political sciences always taught this. Okay, so that is the first thing. And back to sex, we talk about this. Okay, and remember this game is we have two Nash equilibrium, both go to opera, go to football, and in this case, there's not clear there's a Pareto dominance, means that there's no outcome that's better for one over the other. Okay, so what would be the why you have this, right? What is the prediction, right? What's the prediction? What's the prediction? Which outcome? So for you, in case for you, what's the outcome? You predict. For you, what's the prediction? What's the prediction? You think opera or football? Huh? Both of them. But if you want to pick, can you tell? You can't tell, right? Just based on this. Okay. So consider in the movie, I don't know whether you watch it, it's in the 90s, what we call My Barbaric Girlfriend, 我的野蛮女友. Okay. In that movie, so what do you expect? What do you expect? What do you expect? Yeah, opera, right? So you have to rely on something out of the game theory to know. You have to know what we call the institutional structure to make a prediction. Okay, and okay, this is one way to do it, but actually some game theorists don't like it, because if you want to model it, why don't you model that particular background, right? You should also model those things. But I mean for us it's okay. I mean we can just say, okay, institutional structure that make opera the default choice, and that's the outcome, right? We allow that to happen, right? So that end up like here, right? And that actually what happened when the China opened up in the 80s, right? And we let some group of people get rich first, right? 先让一部分富起来, right? So actually what happened, right? There's a rich people, there's poor people, and they let this go over again, right? Now probably we want is the getting rich together, right? 共同富裕, so we go to the other one. So we don't know which the outcome, but I mean if that's the model, then that's what you see. No, it's not joking, but it's just like in our world, right? We not economic, it's allocation of resources, right? So we just decide how things are being allocated, right? Now even the US talk about or the Europe talk about the more socialist movement, right? Like the Brazil is going to be more socialist, right? It's like moving between here and there, right? The labor union or capitalist who is going to win, right? It's going to be like this, right? But anyway, you may laugh, but that is what actually happened at least from my perspective. Okay. And the other one that is also what we call the anti-coordination game. It's called chicken game, right? I think later I will probably send you the list of interesting video you can look at, because there's several movie talking about this chicken game, just like two guys go with each other, right? So the snake and chicken, right? So easily see that, I mean, it's called anti-coordination, means that they would not choose the same action, right? Same action lead to disaster, right? In this case, they collide each other, they die, right? And if they both chicken, actually one will deviate, right? So they want to do this one, okay? And who is going to win this game? Okay, of course, there one winner, one loser, right? And who is the winner, who is loser? Okay, again, this actually fit very well about the I don't know, the political situation, right? It's actually this fit very well. Who is the winner? Who is the loser? Right? You have one item to allocate, right? Either they destroy it or you don't allocate, right? You allocate the object to either of them. right? Is that clear? What's going on? So suppose this actually fit the item allocation, right? So maybe there's a beautiful man or handsome woman, right? Or a very important treasure, they fight, right? And they fight, they die, right? If one get it, one away, then the other guy get the object, right? And this object actually they don't fight, right? No one get the object, right? And you can see that there are two outcomes as well, okay? And sometimes they call the Hawk and Dove game, right? Actually, this is the game actually it's more interesting they look at in the evolution game theory, right? And there is a two outcome there, right? But actually over time, this thing depends on how many people choose this, okay? Say in the game that like hot dog game is like the idea probably to talk about the lion and I don't know, lion and rabbit, right? And you say if more lion, then you have less rabbit, right? And more rabbit, and then we to more lion, so on and so forth, right? So and then you decide evolutionarily how you would survive. But anyway, but that would be a actually very interesting game. I mean, but it's not out of our practice. We don't talk about evolution game theory, okay? And evolution game theory is a very hot topic in the 90s. And now, except biologists or experimental people, actually not many people talk about those. The reason is being they do not offer too many difference, okay? And the idea is like the following, okay? In this model, in Nash equilibrium, we just say people choose this over this, right? And this over this, okay? And what they are doing is related to the next, we talk about mixed strategy. Actually, they talk about is it a evolutionary stable, okay? They will assume, okay, start with this outcome, okay? Every people choose this, okay? And if there's some mutant, okay, evolutionary, the mutation, right? Mutation. There's some people crazy, okay? They choose below. Would they better off? If they better off, then more mutant go to it. Okay, it's a dynamic sense. Okay, we start with here. If they deviate for some of these people, is it going to be continuous? If we continue until no one wants to deviate, no deviation can be profitable. It's very similar to Nash equilibrium, right? But it would kind of refine. You just some Nash equilibrium will not be that stable. Okay, so it's kind of refinement. We'll talk about that later. But that would be something to kill something off. Okay. So this is a present dilemma. We have talked about that. Already tell you the DD is Pareto dominated by CC. Okay. Then actually means Pareto if it's an outcome. Okay. Cannot be supported in this framework. Okay. So that's drive what we learn in the next class. Repeat the game. If we are to repeat this game many times, we are able to sustain cooperation. Okay. So before break, let me have 5 or 10 minutes talk about best response. Okay. And so why we talk about best response? Because this is the way that to make us easier to find Nash equilibrium in general. Okay. And this helps us to prove the existence. Okay. So the idea is, okay, the best response is defined as given other people choose this S, best response is lead to one of the highest payoff. Okay. So do note that the English here is a best response. That means that it's not the best response because there can be more than one strategy that is a best response. Okay, so make sure you notice that it's not a typo. This is explicitly written in this way, okay? Because there can be both strategy is the best response. Okay. And okay, we have to be let some math here. Definition. So function is like this, right? When you learn function, so there's a two set here, x and y. Okay. We call f is a function mapped to x and y. If a point x is mapped to the other set, right? So mapping is just how one set with the other, right? That's what you learn. And what is correspondence here, right? But do remember that you allow, for function, you allow this to happen, right? They can point to the same point, okay? So what is the correspondence? Correspondent actually means you map to a bunch of points, okay? You allow that to happen. So a correspondence means the following, okay? The function here, you can map to a 2 point. Okay, or actually what we call the set value function, or call set value function. Okay, you just map to, you can map to more than one element there. Okay, so why we need that? Because as I said, when other people choose particular strategy, your best choice, so what here is the best correspondence because only have one, because it include all the best responses. Okay, so basically just like other people choose this strategy, okay, give me this strategy. What is beta I is the set, okay, include all strategy, okay, such that this is a best response. Okay, so include every best response. Okay, so very important. It's a set. Okay, it's very important. If you fail to notice this, then you would be unable to do the mixed strategy Nash equilibrium. Okay, so this is very important. It says the correspondence. Okay, and that's important to understand the proof, everything as well. But we're not going to prove, but that's at least you understand why we need correspondence. Okay, and with this knowledge, we can define what is Nash equilibrium. It's what we call mutual best response. Mutual best response. Okay. Of course, same as this, no unilateral deviation, but this is a mutual best response. It's saying that a set of strategy, set profile, right, is a Nash equilibrium if player I, okay, is the strategy belong to the best response, okay, given other people choosing those strategy, okay, given the other people choosing what is the best action that I is doing, okay. And the reason why we write in this way is because, okay, we can write Nash equilibrium as the fixed point. Okay, so maybe I can illustrate this, okay, easily. Okay, later you will see. Okay, okay, this is a little bit tricky. Okay, but let us look at this case. Okay, then you will see what we are doing here. Okay, so this is Carnot oligopoly, right? Or you can say duopoly easily, right? So we define n firms, and we have inverse demand curve. Okay, and the strategy is just like this, right? Cost function, this payoff function. So I define three things here, right? Payoff set, player set, strategy set. Okay, this is done. Okay, so let us see how we can define properly the best response. Okay, remember the best response is talking about at the given, if you produce this, how much I want to produce, right? So it looks like, consider the case we have two agents, two firms. Okay, this is a typical graph. You will see actually later as well. Q1 is here, Q2 is here. Okay, so if you learn, it's just like we call what we have done. Say, in particular case, okay, P is A minus Q, cos is C times Q, okay, the standard case, right? And this is the profit maximization problem, right? A minus this minus C, like QI, okay? The FOC will be just the difference of this, right? And you can solve this out, right? It's this guy, and then you just here, okay? So which means that the best response for player one in given quantity Q2, okay, will be A minus C minus Q2 over 2. Okay, and what does that mean? We can actually draw this in this diagram, okay? So when Q2 is 0, Q1 is A minus C over 2, okay? When Q2 is 0, so A minus C over 2, right? And if Q2 is A minus C, this is 0, right? So A minus C is 0. And this linear, right? So this is the best response, okay? But do note that we have to be very careful. This is not done yet. What happens if Q2 more than A minus C? Here. Okay, this is actually not a complete statement because you should have 0. Right? Because the reason why we have something this here because it's we didn't specify what happened if Q bigger than A, right? But anyway, so this is the first thing. And because of symmetry, okay, you can see we have okay. So this is the clear. This is beta 2. Okay. Okay. So, and from a definition, the intersection of these two line or best response correspondence is a Nash equilibrium. Okay, you would probably see why is the case because at the intersection point, right? Given player 2's choice, player 1 is happy here. Best, right? And same as given for player 2, given player 1 choice, player 2 already the best. Okay. So at the what we call the fixed point, okay, it's because of given this Q1, Q2, it goes to itself, right? So that's why it's called fixed point. Okay. It's because of we can define because we want S1 star is the best response given Nash equilibrium. We want this happen, right? Given S2 star and S2 star is best response given S1 star. Okay, so we can write a S star. Okay, S star is just S1 star, S2 star is a okay, and beta is just beta 1, beta 2. Okay. So Nash equilibrium is just a correspondence map to itself. Okay. That is why we use the math, the fixed point theorem to prove the existence. Okay, because of the idea is at that point, it's mutual best response, right? Already, my choice is best to respond to what you're doing, And same for you, okay? For everyone, okay? So that's why it's a Nash equilibrium, okay? So that is the reason why I talk about this best response, right? And that's how I write it in this way, okay? So, and that's why when you do your calculation, it's always good to draw the graph. The reason why you draw the graph is because you would know what is missing here, right? This is not clear when I write this, right? Of course, this is still well defined, but if you don't draw, you don't know you miss this guy, right? What happened more than this guy, right? Because this, the derivation of this, right, imply this is positive, right? Because negative, right? You have to make sure that this is not going to be anything negative, right? Because you have the always choice not to produce anything, right? So that's why you're bounded by 0, right? So that's why you have that guy, right? Because make sure that you're not producing, then otherwise you keep going, right? You can go to negative, you can keep going, right? So you make sure that this is a constrained one, right? Because QI must be positive, right? So you cannot allow negative to happen. Is that clear why this is the case? It's because of you can't go further. Your quantity cannot be negative, right? Otherwise, you will keep going. Okay, let's have a break of 10 minutes, and then we will talk about mixed strategy, and that's end this topic. We'll talk about multi-stage game. Okay. This is defined for every possible thing in the choice set. This Q2 gap. So as I was just comparable one comparable. So you tell me what is the best thing they have to do.
can be something very crazy. So that's why it's possible. Sometimes equilibrium can be something crazy, something maybe positive, there may be something very bad, right? So it's still very easy. Okay. To be very careful. You often don't notice, that's why you write that explicitly this guy. So otherwise you do this. Okay. Yeah. Okay. ID minus in the body. A minus. A minus minus. Including ID minus something.
Okay. I hope you have a good break. So let's continue. So is it okay? So we see this is the point where they coincide is the Nash equilibrium. In this case, you need one. Okay. And it pretty much can make sure it's unique, right? There's no other Nash equilibrium because this how. Yeah, here I'm not. I think I should also draw this. It's not perfectly correct, but I mean, but I think you get the point. Okay. So some of you actually asked me how you do Bertrand, right, in the assignment. So actually, you can also do this best response analysis. Then you would know actually what is the Nash equilibrium, right? When you actually don't know what to do, start Nash equilibrium, just consider what other people can do, right? Give other people what is the best I can do, right? And look at the intersection, it will be the answer. Okay, so that is the easiest way to figure out what's going on. Okay, you can try this at home. Maybe I make assignment or whatever. Okay, so I mean, just how this Nash equilibrium related to dominance. Actually, they if there's only one that left from that process is Nash equilibrium. Okay, and Nash equilibrium always survive. Okay, and that means the following. If you try to so if you have iterated elimination of strictly dominant strategy, and you see. Okay, so and if it's a unique survivor there, okay, then it will be inside. If there's a unique survivor, be inside. Okay, so if you keep eliminate, then you will be okay there. Anyway, so that means what you can if you solve Nash equilibrium, you can pretty much forget about strategy that are strictly dominated. Okay, so that's why I draw in this way. You can basically ignore this part, right? So that's why when I draw, sometimes I just being lazy, but you should be careful. Okay. Yes. Yes, we have. We'll talk about that at the end of the slide. We will have a condition for existence. Okay. So as we said this one, right? Rock, paper, scissors, a simplified version. We don't have equilibrium, and that's actually what we do is what we are actually doing is randomizing over head or tail, right? With a half and half, right? Equal chance. That's what we usually do, but this is not consistent with what we say. We have to choose an action, right? So we have to relax our strategy profile, strategy set. Okay, we allow mixed strategy. Okay, do note that this relaxation would make sense for some game. It doesn't make sense for a lot of games. Okay, mixed strategy. Okay, is a good trick that is useful for many scenarios, but in some cases it's not really making sense. Okay, it will make more sense if you consider case actually repeat several times. Okay, or in some scenario you are actually mixing. Okay, so the idea is the strategy now is not the strategy choice SI, the strategy set, but rather is you would assign probability for each action. Okay, before you just assign a degenerated probability, right? You just put one into one of the choice, right? So what? Maybe I just wait this, right? So before, what's the strategy? If I like this, right? Say, in this case, I have strategy for one, is set equal to head and tail, right? It just, the strategy is just S1 is either head, right? Or S1 is tail, right? Either this or that, right? But now it's not about this, but rather we S1 is two number here, okay? It's number, say P1 and P2, okay? And P1 plus P2 is equal to 1. And P1 bigger than 0, P2 bigger than 0, right? So which means that maybe P head and P tail maybe is easier to. So this means that I would have this probability choosing the head, this probability tail, right? So that is exactly what's going on here. It's a probability distribution over your strategy, okay? And so you put probability over all the strategy, okay? And you can easily see that if the strategy set is the discrete, that is easy to describe, right? Because the probability mass. If this is continuous, things become very complicated, okay? So we focus on the finite game. In general, finite game means the finite strategy. If this is a continuous game, continuum game, or infinite game, that things can be very complicated. You're mixing over a continuous interval, then the problem is usually the existence. Okay, but we focus on the discrete case. Okay, and here the utility, okay, because you're randomizing, okay, so and what is the outcome is because depend on randomization outcome. So you are doing the choice under uncertainty, right? Because you don't know which outcome comes out. So here we have to talk about expected utility, okay? And yes, what is M is the probability. In this, it just here is if you note M1, M2, okay, is the probability that assigned to that strategy. You multiply by that. Okay. Reason why? Okay, maybe this is a little bit clumsy, so let me write this case. Okay. So let me write a matrix, then you understand this notation. Okay. So pair 1, pair 2. Okay. Pair 1 is strategy 1, strategy 2, say. Okay. Pair 2 also has S1 and S2. Okay. So what is the strategy? Okay. Before is choosing this or that. Okay. But now we will have this is the we will be choosing is M1 of S1. This is M1 of S2. Okay. And this is M2 of S1. This is M2 of S2. Okay. And here, a very important assumption we make here is they randomize independently. Okay. So that means that this outcome would appear because independent, right? Then that means this outcome would appear is S1 times M2 S1. Okay, so here comes, that's why this guy. You are just for each randomized over there. Okay, is that clear?
thinking of probability, is that still okay?
No, you are random. Okay. Before the game here is before we only ask to choose either S1 or S2. Now we're asking you put what's probability of S1 and S2. That's it. And your payoff is given instead of this outcome. It depends on what's realization. So no, you know, okay. Suppose it is simple, very simple. This is head or tail, right? If this half, this half, this half, this half, say, what's probability of this? One quarter. Why? 1/2 times 1/2. Is that clear? So just like you put it this way, okay? We just do rock, paper, and scissors, okay? It's simple. Another example. Let's do another example. Okay. Put it this way. Okay. Rock, paper, and scissors. Rock, paper, and scissors. Okay. Suppose you are very smart. You do 1/3 of this, 1/3 of this, 1/3 of this. Okay. Suppose I'm dumb. I only do rock. Okay. In that case, when we have rock and rock? 1/3, right? 1/3 of this, 1/3 of this, and this are 0. Okay. If I am not that dumb, I suppose I do is I have 1/2 of rock, 1/2 paper, right? That would be 0, 0, 0. That would be 1, 6, 1, 6, 1, 6, 1, 6, 1, 6, 1, 6.
So this part based on the assumption that none of these choices is dominated by other choices.
So you just the assumption is they randomize independently. So just like the following, okay? Two guys come together, they do rock, paper, and scissors, okay? And they look at there's a randomizing device, right? Maybe just a number or whatever, pros and cons or whatever, and decide what to take. And how I randomize it independent of the other guy. Is that clear? So what's the question here? You can use Chinese if you want. Oh no, you're allowed that you're allowed to dominate. There's no restriction on the strategy. Dominance is another idea. Okay. If it is dominated, okay, we will show you will never include in your mix. That is something we will derive. But in defining strategy, you can randomize over dominated strategies, fine. But you are right. I mean, your prediction is correct. If something is dominated, then you will never be randomized over them. Okay. I hope yeah, that's easier. So if you, yeah, it's okay. So the only change is you allow your strategy space to expand. Okay. Before you just choose one of those, but you're now over randomized all of them. Okay. So that means that the Nash equilibrium also the same idea, right? Just like given my randomized strategy, mixed strategy, you just no other strategy is better off. Okay. And because of that definition, you can easily see that if one strategy is better than the other, okay, if one strategy is being strictly dominated, you don't randomize over them, right? Because randomize over them because they will realize, right? And you do randomization, obviously worse. So that means that when you try to construct a mixed strategy Nash equilibrium, you should first remove the strictly dominated strategy because they will never into your action. Okay. So that is the consequence. But I mean, you're right, but that is not in the definition. But you're right. When we look for the mixed strategy Nash equilibrium, yeah, you can take on. So we will illustrate in example how you find a mixed strategy Nash equilibrium, and you can see it turns out it is very complicated. Okay, and I think in decision science actually there's a people design algorithm to find this problem. Okay, this is a computational problem. How you can find this quickly in a large scale problem. Okay, and find Nash equilibrium is not a trivial exercise. Okay, especially allow probability, because say when you have two outcomes, right? Actually, you just have only one dimension, right? Add to one. When you have two or you have three strategy, you already have two numbers there, right? With two simplex. So you have two-dimensional problem, right? Finding a multi-dimensional fixed point is a very complicated idea. Okay, but anyway, let's see why it's complicated. Okay, so very simple example, matching pennies, right? And how do we see the mixed strategy is player one, head or tail is mapped to 0 and 1, just put probability there. Okay, to be simple, just one variable, right? R is the head for this Q, R and Q, right? R is here, 1 minus R, Q, 1 minus Q. Okay, so that is what it means. And we start from scratch. Okay, so what we are doing is the standard way to do. Okay, so just clear how we do it. I don't know how you learn in undergrad, but this is the way you should do. Okay, this is you have to calculate what is this is very important. Equation is to tell what is the utility. You choose it M1, right? You M1 X1 M2 X2, you get H, right? So there are 4 possible outcomes. Okay, maybe write down here to make sure that you see what's going on, right? So it's actually you have H and T, you have R, 1 minus R. Maybe I use another color. Okay, just 1. Just 1, and this is R, 1 minus R, right? And this is Q, 1 minus Q, right? This arises when we have Q and Q, 1 minus Q, 1 minus Q, right? And we have R, 1 minus R, 1 minus R. Okay, so that's why for you it's RQ times this 1 is -1. -1 comes from this entry, right? H is -1. Okay, so you have to do for every single one. Okay, you can see if the game is complicated, there will be a huge object. Okay, but if you use mathematical or other thing, it's very easy. You can derive this is the answer. Okay, so now the question is a little bit, okay, have to be very careful here, So you are choosing R to maximize this, holding Q constant. Okay, because you are find the best response for every possible Q. Okay, so you're doing a partial differentiation. Okay, Q is exogenous. Given the Q, what's the best? Okay, so that's why what you're doing is you do a partial differentiation. Okay? Because looking at given Q, what's the best response, right? So the best response, we solve it, right? Negative is here, right? Oh, you just this 2, right? And so don't go too fast by equating to 0. Okay, don't go too fast. Okay, so you have to look at more than, equal to, less than. It's very important. Okay, because of the idea of boundary solution. Okay, If there's no boundary, equal will be fine. But your boundary, okay? Because Q can only go from 0 to 1. Okay, so have to be very careful. So here we show is negative, right? Q, if Q is 1/2, then you're done, right? Usually that's usually you get, but have to be careful when it's positive. If Q is very small, less than 1/2, this is positive, right? When Q is, so let's draw this guy. So you have to be careful, right? Here is positive equal to 0, less than 0. If right? So what does that mean? It means that if Q is less than 1/2, you would want, look at this, you want R as large as possible, right? What does that mean? We have boundary, right? So your R will be 1. This, the R will be 0. So that's why when you try to draw this guy, you are R, they are Q, right? From 0 to 1, from 0 to 1. If, let me use the blue color, okay? If this is 1/2, okay, turn out to be, okay, there's no R here, right? So anything is fine, okay? So it means if Q is 1/2 is here, anything is fine. So here, okay? If Q is less than 1/2, you always go to 1, right? If Q is more than 1/2, you got 0. Okay, so this is a with symmetry, okay, because it's a symmetric game, I don't need to do it for a second one. What you will see, I forgot the 1/2 here. Remember, write down this is best response for 1. Okay. Actually, this is the given Q, right? And you would what you will see this won't happen, right? Just flip. Oh, maybe I just derive it. Otherwise, it's better to derive it. Okay. So this is what I have in this line. Okay. And if you derive this, okay, this essentially said, right, when R is 1/2, you still do whatever you want. When R is more than 1/2, you want to positive, you want to go to 1, right? So this is the result. So when R is 1/2, anything is fine. When R is more than 1/2 is 1, so it's exactly this guy. Okay. So you can easily see that the only possible Nash equilibrium is here. Okay. There's no other thing. Okay. Because you fully characterize it. So this is the way that you never miss anything. Okay. So make sure that when you try to solve, you start from the first principle. Always start from the best response and try to figure out the mutual best response. Okay. Don't do the shortcut. Okay. Because usually when you learn undergrad, they will tell you they will try to do under this Q, this is a payoff, right? And then you will try to see this equal to this, right? But anyway, that is the best way to handle. Okay, so that is the graph. And this only result. Okay. And we want to go over this one, okay? Because this is very important to show you this method, okay? And this is 1/2. This is the battle of sexes, right? You know these are the equilibrium, but actually there exists an outcome that I think is more fair, okay? Which is they randomize over opera and football, okay? And you can see if R and Q, so R minus R, Q and 1 minus Q, right? So it's 2 times RQ and 1 minus R and minus for 1, right? Because these two you can ignore, it's 0, right? Because it's R1 minus R, Q1 minus Q, R times Q, 1 minus R minus Q. Is that okay? So that's you get this payoff, okay? And you do the differentiation respect to R, right? Because Q is the boy's choice, R is the girl choice. So you differentiate respect to R, okay? That is given to this one, okay? And let me draw this here to show you how you draw it, okay? So this one said the following, right? This is R, this is Q, okay? And always from 0 to 1 in this context, okay? So for player 1, okay? In this particular case is here we don't have anything for R, right? So the FOC is independent of R, okay? It really depends on Q only, okay? And if Q is 1/3, okay, R doesn't really matter because always 0, right? So it doesn't really matter which one you choose. Okay. And if Q is more than 1/2, so 1/3, then you would choose the maximum R, right? If Q is more than 1/3, this is positive. You want to increase as much R as possible. So R possible, right? Increase as much as possible is equal to 1. Let's see. Okay. Otherwise, it's equal to 0. So it looks like this. Okay. So this is the girls. Okay. And what is the girl? Okay. It's not symmetric, so to be careful. Okay. So RQ is, this is the opera, right? This is football, okay? And player 2 choosing Q, so we would differentiate with respect to Q, right? So it's just -2 and 3R, okay? And here you can see when R is 2/3, okay? When R is 2/3, then you would be indifferent, right? When R is 2/3, you'll be indifferent, like this, right? When R is more than 2/3, you would be choosing as high Q as possible, right? So it's 1. Otherwise, it's negative. Okay? So you can see, as we expect, there are 2 pure strategy Nash equilibrium here. Okay, the pure strategy, and there's a middle guy that is purely mixed strategy. Okay, so actually we have 3 equilibrium. Okay, you have to be careful what you're looking at. Okay, so I guess what is left is not calculation, but just a bunch of results. So this is the Nash equilibrium, this is the graph here. So want to give the interpretation of mixed strategy equilibrium. Okay, And when I try to mix things here, you mix is must be to you are mixing them, right? You are tossing a coin to decide what to do, right? It means that it doesn't really matter which one you're choosing. If one is strictly better, then you would have choose that. You would not toss a coin. Then repeat. If you are randomizing, say rock, paper, scissors, okay? You are randomizing, right? And it must be the case when you randomize, these three of them actually no meaning to you. If it's clear that rock is always better, you just choose rock. Why randomize? Why would try to toss a die, roll a die, to let the nature decide for you, right? It must be the case to you the same. Okay. And probably the question is, if that's the case, if every action is same to me, why randomize? Why just choose one? The reason why you want to randomize is because you also want, when you randomize, you make sure the other guy also indifferent. So like this, why you want to randomize rock, paper, scissors? Because when randomize, for the other guy also randomize as well. And for him is independent. So it becomes equilibrium, because when we do randomize, it's no effect on my payoff, but you affect other people's payoff. You make other guy indifferent. It's like here, as I said, right? I randomize, it's because I make you indifferent over your actions, your choice, okay? And that means this indifference will make it optimal to randomize. And we both randomize, then we don't want to change, okay? So because of, just like this is a zero-sum game, right? If I win, it means you lose. Because I don't want, because it is, you always want, if you know what I'm doing, you always have a best thing to do, right? So we have a conflict of interest. So in order for this conflict of interest to resolve, it must be the case I make sure that, to randomize, I randomize to make sure that that's head or tail, right? I randomize over head or tail, then the player one is indifferent of this. But it randomize over this, also make sure that player two randomize is meaningful. Okay? So this is the reason, okay? So that's why when you learn undergrad, usually shortcut like this, right? You will try to make sure this is the same, right? And sometimes they tell you, okay, how can you decide these two, right? You just make sure that this payoff, right, is same for these two, right? So usually when you're undergrad, they teach you how to solve this problem, right? How will you solve this problem undergrad, right? So usually they will tell you the quick shortcut, okay, is opera, football, right? It's R, 1 minus R, Q, 1 minus Q, right? So it's 2, 1, 0, 0, 0, 0, 1, 2, right? How they teach you, right, undergrad, right? We'll be doing that. You're indifferent over this and this in a pure strategy. That means that if you use pure strategy, this one, the payoff will be 2 times Q plus 0 times 1 minus Q. This is the strategy payoff under opera, right? And you can also look at payoff under football will be 0 times Q plus 1 times 1 minus Q. Okay, this is 2Q, and this is 1 minus Q. Okay, and is that clear what I'm doing? Okay, so if you talk about mixed strategy, you're mixing over these two. It must be the payoff the same, right? Because you're randomizing over this, right? If they're not the same, why you randomize? So it must be the case 2Q is equal to 1 minus Q. So Q is just 1/3. So this is shortcut. If you know that he's going to randomize over these two. Okay. If you already know they randomize over these two, you can use this shortcut. Okay. If you don't know, this shortcut is not good, right? Because if you do this shortcut, you will omit the corner solution, right? One, because this is only This is only feasible, right? This is only correct, right? When you talk about mixed strategy, right? If you do this, you forget about these 2 points. Okay? This is only true when you truly mixing strategy. Okay? Is that okay? Is that clear? Why this would work? Because other people randomize, okay? If you randomize over these 2, it must be the case that this to the same. So that's how you find. Is that clear? So this is the shortcut. Usually you taught in your undergrad. That's how you do the. But I mean, I teach you this way. This is the formal way. You don't miss anything. Okay, so this is the more preferable way. I mean, this is you teach your undergrad. Okay. Now, I guess I want to mention this before I break because someone want to know existence, and probably everyone want to know anyway. So we focus on finite number of players, finite number of strategies, okay, and which is called finite game. And actually, this is actually a famous theorem by Nash, right? If you look at Beautiful Mind, I don't know whether you know Beautiful Mind, John Nash. This is his contribution, which in his undergraduate thesis, he proved always exceed a Nash equilibrium in mixed strategy. Okay, and because before that it was Morgenstern with Neumann, they have the game theory. They only study zero-sum game or constant sum game, and he comes out and say, okay, what happened when we talk about mixed strategy? Right, that's his contribution. Okay, he proved existence, and of course he didn't actually when he did the proof, he didn't know there exists a fixed form theorem. Okay, and he bring his proof to von Neumann. When Neumann just say just go home and this is just fixed form theorem. Okay, he didn't realize this is so important after many decades now. Actually, everyone use it, right? But that is the idea, right? If you think that rock paper scissors should have equilibrium, then you are following what Nash thinks. Okay. And the second one is what we call the infinite game. Okay, each also proved in by De Bruyne. Okay, and the condition for existence is not difficult. Okay, what required is the strategy set a compact and convex. In general, it means if you choose a interval, yes, right? You choose from say a production from 0 to 10, yes, okay, and for compact and convex, you don't have open interval, right? If you have a positive, then it's a problem. But as I said, when you do production, right, you cannot produce infinite amount anyway. For consumption, called the demand curve, right? You always bounded by somewhere, so it's not a problem. And your payoff is continuous in other people's strategy. I think it's in a lot of cases natural, right? If the production of your opponent change a bit, your payoff will change a bit, right? That's what continuous means. Okay. And do note that this is not the case when we talk about other scenario like auction. Auction is not continuous because suppose you and your opponent, okay, are same price, okay, or a little bit maybe similar, right? And the other guy changed the payoff, change the bid, right? You may matter win or lose, just epsilon change. So either you get win or you get lose, right? So the payoff change is good. Like Bertrand, also the same, right? Maybe this is Bertrand, right? Bertrand is a case where if my price is the lowest, I've got a grab of the market, right? But if the other opponent suddenly reduce the price epsilon, I lost everything, right? So if my price is here, right, the other is here, then I got positive payoff, right? Suppose the price is beyond C, right? But if the opponent just slightly reduce it, then I get nothing, right? So this is look natural, right? But in some scenarios, not. Okay. And this usually is fine. Say your payoff is continuous and concave in your strategy. Quasi-concave is rather weak, right? We learned that. Okay, quasi-concave is not very strong. Okay. And many things satisfy quasi-concave. And do note that this is only sufficient condition, okay? If you release some of them, it will be some more result. And probably ask what happened when you have this continuous, and there are many theorem that has been proved. How to relax this? Okay, how to relax all this as a active research, because there are many scenario like context that would rely on this. Okay, because in context, right? Just like the Olympics, right? The one who run the fastest win the game, right? And slightly faster, then it will be different, right? This continuous is something very natural. Okay. So I guess there's a break. After the break, I'll talk about the last model, which is called the variant model. We try to relax the idea of Bertrand competition. Okay. And you will see that when we allow mixed strategy, and we have something interesting goes on. Okay. And then we'll end this topic. Okay. Let's a break. 10 minutes.
我的学习嘛，我在教我上了一个学期，他教我在参与 return the base and then from the right. Very easy to understand. Something to make it to self contained. I need to go back to the paper. Very easy to make it understand. Otherwise, I have to read those papers. Which one is two of them? They don't just say according to definition, two of them.
So let me quickly consider the variant model. Okay. So this is related to a paper I recommend you read is how to build the model in spare time. So how can he think about this thing? Is variant now I think it's the economist in Yahoo, no, or Google. I don't know, I forgot. The chief economist in I think Yahoo, I think Google. I can't recall. Anyway, one of the top. And how he think about this model is at that time in the 80s, he want to buy a TV, a big TV, and he's in US, okay? And he, as an economist, right, he want to buy a TV in the cheapest price, right? And then he visit the store. At that time, there's no internet, right? There's no internet to check, okay? I have to go to the store and check. and you drive, right? Drive a long way to check and drive a long way to check. And he just have look at the price, okay? And he figure out that the price of the same store is not constant. Okay? Maybe this week is 1,000. The other week is 2,000. And the other week is 1,500. Okay? So he built this AER paper to try to explain why a firm is keep changing the price. Okay, for marketing people, they will have some reason why they do it, right? Marketing people will say, okay, they do it because they want to look at the elasticity of demand, right? Because they change different prices, they can look at that, okay? But he's not looking at this perspective, okay? Just simply try to see, is there any strategic reason in the game theory this will make sense, okay? And if this he worked in a Bertrand model. If you recall, in the Bertrand model, price competition will lead to zero profit. Okay, so what he do is try to see, actually later you see the next strategy will try to avoid this problem. Okay, so let's see what we do. Okay, in this model, actually what he do is try to consider the idea that not all the consumers are the same. Okay, one type of consumer is informed, the other one is not. Okay, so why they do this is actually at this time, information economics is very popular. So actually, you look at those days, actually people doing search theory, people actively search. That is anyway. So in the model is some of the consumers won the mass. Okay, and it's very simple model. There's no demand curve. Everyone have unit demand. If you get the unit, he will get payoff of V. Very simple, right? If I pay the price, V minus P. Okay, so basically is the payoff is very simple. I should have written down somewhere. It should be the payoff of the consumer. It's like this. U, okay, V minus P if buy 0 otherwise. Okay, so I should have written down there, but and everyone only have unit demand, so it's very simple. Okay, and the Bertrand comparison with marginal cost. Okay, so you expect, right, marginal for Bertrand, you would expect the price is C and that's it N, right? Standard model, right? Whether inform or inform doesn't really matter, right? Just you go to this store, go to the other one, right? So here the firm, okay, I just restrict to C to V, okay, because charging below C is going to lose money, so there's no point, right? Charging beyond V, no one will buy it, okay, so it doesn't really make a difference, right? So let's focus on this case, okay. I mean, if you more than V is 0, right? More than less than C would be negative, so that's okay to focus on this one. Right? Is that clear? Okay. So if your price is higher than any one minimum, so you're not the lowest. Okay. So what you get is you only get your uninformed consumer, which is your diehard friends, right? You can imagine iPhone, no matter what price, as long as not more than V, some people will buy. Right? Those are the diehard friends. Okay? Because the N firm, so you get everyone get U over N, right? But if you are one of the lowest, okay, you also get people who keep searching. Okay, if there are K, many of them are over K. Okay, you know the setup. So let me repeat. The setup is let's look at the graph easier. Okay, so there's a informed or uninformed. Okay, the N firm, so everyone will get a share of this. As long as your price is not more than V, they'll come to you. Okay, this is a lock-in consumer, right? They keep purchasing from you. Okay, and This guy only go to the lowest price. Okay, that's like Bertrand, right? If multiple lowest price, you just equally split among them. Okay, if only you go on to get it. Okay, so what this model would looks like, right? This is like a simplest changes to the Bertrand model, right? You just add some consumer, they always come to you. That's it, right? They always come to you. Is that okay? So what is your prediction, right? Would that be everyone charge C is the answer, right? It's possible, right? Everyone charge C, yeah, right? If everyone charge C, is there any way to deviate from that? Is it everyone charge the equilibrium? In this model? Can you tell me? The answer is no. Why? Because if everyone charge C, you charge V. Because you have your diehard friends over there. Right? You have people you can exploit. Okay? So that's here means already one thing is if you have some consumer, actually that is, I don't know, is uninformed, okay? Lock in, then Bertrand paradox is gone. Right? So if you have someone who is, yeah, always buy from you due to convenience or due to for whatever reason, brand recognition, or whatever marketing people is doing, right? Even Bertrand competition would be avoided. Well, that's the first observation. Second observation is what is this model deliver? As I said, you want to deliver the idea why the price keeps changing. Right? So I'm not going into the detail, okay? I'm not going to prove it, okay? So what is said here is no firm is going to set a fixed price. Okay? Firm will randomize from V to C. At a firm, they randomize over V to C. Okay? Why? At V, you will try to you will try to exploit. You are forget about the informal guy. You just try to exploit this as much as possible. Right? And why you randomize over lower price? Because you will engage in competition, right? Because some people come to your store and will just buy it. Right? The reason why they're willing to buy at the price higher than C is because everyone is randomizing. Right? It's possible that everyone is randomizing. Okay. And there's possible that I'm the lowest, right? But not at C. Okay, let me repeat the statement. Because everyone is randomizing. Okay. Suppose the simplest case is you and me. Okay. We're randomizing. And because we all randomizing, it's possible that we randomize in the case I have a price higher than C, you also higher than C, but are lower than you. Okay, that's better than Bertrand. Is that clear? Let me repeat the statement. Okay, I mean, of course, you can look at the proof, but the idea is very simple. Why you want to randomize? Okay, because it is possible that we randomize above C, and in the case that we all randomize, we all above C, I can still sell the product, right? Because I randomize, right? And you also randomize, right? And you randomize, actually, it doesn't matter which price I'm charging, right? But by we all randomize, then we avoid the worst case scenario, right? Kind of. Okay. But I'm not going to go to the proof, okay? Although the proof is very simple, and turns out that this is the implication. There will be a you need symmetrical equilibrium, that you will charge the maximum price, okay? And the minimum price, of course, is not C. The minimum price will satisfy this constraint, okay? Because you will be indifferent between the highest price and lowest price, okay? So the higher price, this is your payoff. This is your lower price. Lower price, you will always get everyone because you are the lowest already, right? Because it's mixed strategy. The probability that everyone is more than one guy having the lowest price is 0. So you set the lower price, you will get the whole market. Okay? So these two characterize what's the maximum price and what's the minimum price. And you can easily see that this is not C. Okay? So basically you escape the Bertrand paradox. Right? So you will see everyone charging the highest and also somewhat also highest. And you can see this is also depends on I, right? Higher the I, lower this guy, right? If people are keep searching, a lot of people are searching, then this will be very low, right? You see that, right? And you I go to 0, right? This go to V. Right? Because you can easily see, right? If no one is searching, right? You can just charge V to everyone. Right? Is that clear? Actually, this is not is a very interesting result because it explains why firm is not charging a fixed price over time, right? It explains why when you 1 week you go there's a price, other week the other price. Okay, this also explains why you go to supermarket, A is supermarket B. It's not clear that every good in supermarket A is lower than B, right? In some supermarket, A for some item is lower, for some item is higher. Okay, somewhat along that line. Okay, so that is even say suppose you go to a store that is famous for low price like Walmart, it's not every single price is lower, right? There may be something that's higher. Okay? That actually explains, right? The randomize over different thing. Okay, but anyway, I hope that you can check the proof. It's not everything there is not beyond high school math. Okay, there's no complicated math is being used. It's just an elementary argument, but I don't want to go into that because of the time constraint. Okay, just to give you some idea, because we're not doing IO, so it's not very important, but just put there. So I want to talk about this, what we call refinement of Nash equilibrium. As we said, it's possible that we have many equilibrium. Okay, and the problem is how can we take away those not so good? Okay, so actually, as far as I understand, and there's the also usually these 4 actually I use it in my papers, is what we call Chamberlain-Hand refinement, and this what it means is the following. Okay, so you have a strategy, say A and B and C and D, right? Pair 1, pair 2. Okay, here I talk about a pure strategy. Okay, pure strategy game. Okay, so what do you mean by Chamberlain-Hand refinement? Which means that suppose this is equilibrium. Okay, assume this Nash equilibrium, and the question is, does it survive the Chamberlain-Hand refinement? Means, okay, I have a Chamberlain-Hand. Okay, I know how to choose A. Okay, in most likely, but my hand is Chamberlain, so I just have a very small probability I will choose B. Okay, and it's because I keep Chamberlain, right? I will say, is the Chamberlain-Hand converge when say I consider a mixed strategy equilibrium, and I take epsilon to 0, is it going to survive? Okay, this refinement. So that's like I may make mistake, right? I make mistake. Is it going to continue to be true? Okay, if you try to this. And what does that mean is trying to remove weakly dominant strategy. Okay, weakly dominant strategy means that their strategy, say suppose this is say this is 4, 4, 4, so weakly dominated means this one. So you replace this by this guy. Okay, so like this, B is weakly dominated by A. Okay, this is already when you choose D, right? B is worse, but A they're the same. Is that clear? Because strictly dominated means have to be strict, right? It's 5, then it's strictly dominated, but 4 is not. Right? Is that clear? Okay. So, and you would often want to apply the Chamberlain hand refinement. Okay, and you would remove the weakly dominated strategy. Okay, and this is often used in practice. Okay, sometimes they don't call Chamberlain hand; they just say, assuming players would not choose weakly dominant strategy, and that's it. Okay, and second one is just you use the Pareto dominance idea. Okay, remember the stat and hunt, right? And the stat and hare, right? Just like the, remember this one, right? This game. There are two outcomes here. This outcome is uniformly better than this one. So we assume that this one will be the outcome. Okay, and there may be some reason they can collaborate somewhere, right? Because it's good for everyone, right? So it's a strong reason they have some way to go there. Okay, and what is strong reason we will talk about with the game. That would be one way to justify this, but without going into that, there are some people who think this is more likely this one. That's it. Okay. And the other two is, this last two is a much stronger version than what we have, right? Because Nash equilibrium is asking the outcome, no one want to deviate by themselves. Okay. Then strong equilibrium by Ottman, 1951, I think, is 51 or 60, I don't know, something like that. Is talking about they can jointly deviate. Okay, they go together and deviate. Okay, so that means that is you always eliminate this guy. Okay, but the problem of this is too strong, because in most cases you don't have strong equilibrium. In most of the scenario. Okay, say Conor, Bertrand, none of them have a strong equilibrium. When you have most of the competition, you don't have strong equilibrium. Even Conor. Okay, so that's a problem. So that's why in the 80s, someone comes idea we call collision proof. It's a 1987 in a jet. So what it said is immune to credible joint deviation. Okay, so what does that mean here? The definition is very simple. Okay, although mathematically complicated. It's just like you ask if some of us want to jointly deviate. Okay, we come together, we say, okay, let's us choose this. Okay, and what we require is after we deviate, no one to deviate again. Okay, let me repeat is we said we coordinate to choose this one. Okay, but after we do it, no one want to further deviate. Is that clear? Is that clear what it means? But the definition is super complicated, okay? Because it's defined recursively, right? What is meant by not further deviate, right? So you define if only one guy, you can always credible. Then you define two guy deviation, right? When you two guy deviate, no one guy want to deviate. There's three guy deviation. I talk about four guy deviation, right? Four guy deviation will immune to three guy deviation, two guy deviation, and one guy. So the math is very complicated, but this is very useful because Carnot equilibrium will survive this idea. Okay, there exists a equilibrium. Okay, in Carnot model, usually you can see that that can survive the collision proof refinement. Anyway, but do know that these are Nash equilibrium. Okay, just use it when your Nash equilibrium has too many Nash equilibrium. Okay, so you would be refined. But if your game have unique outcome, then you don't need to bother. And the next thing is what happened when doesn't exist. Okay, there are many ways to do it. Is the first one is called epsilon equilibria, which often used in computer science. Is here we have a very big requirement saying that people will deviate, even though another outcome would be better by epsilon. Okay, so we just require that if the gain of deviation is just epsilon, then he will not deviate. So the idea is technically means this. We just equal so the only difference is it's just this guy. I just allow minus epsilon here. Okay, I allow it to have epsilon margin of error when we decide whether to deviate. Okay, and you can choose how big the epsilon is. Okay, and then you have equilibrium, right? Because epsilon is big enough, everything equilibrium, right? When epsilon is infinity, then everything will be equilibrium because everything you can allow to make difference, right? So when you, especially when some of you mentioned there's no equilibrium, that's one way to do it. You allow it, I mean, even though there's some difference, you keep your strategy. Is that clear? So just this one, okay? This is very useful, especially for computer science and things, right? Because you may not equilibrium exist, right? You allow people to stay where they are. If the gain is not big, you keep what they're doing, right? I think it's more behavioral style, right? You just don't want to move, right? If you work, you've been working, you work, you continue, right? And here, this one is very simple. The idea is, I said I randomize. I randomize is independently, okay? Can they randomize coordinately, right? It means that maybe we have public device, okay? We see the sun. Today you have sun, we go to opera. If today is rainy, we go to football. Why this is better? Because we never miss, right? Because remember the mixed strategy. It's possible that by randomization, one guy go to opera, one guy go to football, right? But if say we coordinate, the sky is bright, football. Sky is not so good, opera. We never miss. There's no way you get up in n is 0, 0. Right? So in that case, you can help. Okay. And this correlation proof equilibrium is correlated, just a correlated version that is immune to join. Okay, it's just like we do this, but we still allow it to deviate together. Okay, so these are the methods used. I mean, some of them will be useful, right? Because especially those people who do operation research or marketing, do the computer science style or platform. This can be useful. Okay. Is there any question? I guess this forms the foundation of what we are doing, and that will be very important. Any question? No? Then let me quickly talk about the dynamic game. Just give you overview because I don't have enough time anyway. I'm sorry, a little bit slow, but I guess it's good to have a solid foundation for the normal form game. So don't worry, even though I finished one topic, I would combine the assignment for these two topics and into one single assignment. Yes, okay. Don't feel bad. I mean, I can give you assignment if you want. But I combine it too. Okay. So that is difference of this and the previous topic is people will take action in different point of time. Okay. Before we are talking about they took it at the same time. Okay. By same time, it means that it doesn't mean they do it at the same time in the physical world. It just means that when one makes the decision, the other doesn't know. Okay, they don't know the other decision when they make. Okay, here we talk about the case where people make decision sequentially. Okay, you would usually know one make decision after the other. Okay. So here we talk about the first game that would be interesting to see is dynamic means they take decision different point of time. Remember we have matching pennies, right? And we have saying if the pennies match, okay, player one would lose. Okay, remember the game, right? Just go back to this matching pennies game, right? If the game the coin are the same, player one lose. If the different, player one wins. Right, it's a game. And consider the case where player one move first. Okay, player one sold the coin first, and player two sold the coin second. Okay, or just rock paper scissors. You go first. Okay, so what happened? What you predict? Player two wins, right? For sure. Right? You play rock paper scissors, you go first, right? And then I must win. Right? There's no way I lose. Okay, so that means that the timing is very important. Okay, so but this is what it means, right? He saw it, and then player two follow what player one do. Okay, but there's a complication here, right? Because of player one move first and player two move second. Player two, the strategy is not simply an action. It's an action depend on what player one has been done. So it's a function rather than a strategy. Okay, I'll talk about pure strategy equilibrium. Okay, pure strategy. Okay, is if player one is a head, player two will be a tail. Right? He see a tail, they will choose head. Okay, because player two want to be different, right? He win the dollar. Okay, so that is okay. So that's why the strategy for one still head and tail. But strategy two, okay, you have to choose when you see head, it's going to head or tail. When you see tail, it's tail or head. Okay, so it's a function. Right? It's a the choice actually have two choices, right? So that's why when we define formally for the extensive form game, is very complicated. If you look at Rennie or any textbook, it's very complicated. I will take the version that is least complicated. Okay, but don't worry. I never see any paper actually formally define it. Okay, so although I write down formally here, but no one actually write in the paper. Okay, but you implicitly you define it. Okay, so make sure that when you define implicitly, everything is there. Okay, no one write in this form. Unlike the normal form game, someone would still write the formal way, but I never see any paper write in this form, except in textbook. Okay, so but make sure that what is clear in your model is you have to define all the players. Okay, the second one is history, what has been done. So in the past, what has been done, you have defined what are accessible to the players, right? What do they know? And then here is complicated because of depend on what has been done, we will decide who is going to move next, right? Then that is the player function, okay? And this Z is the terminal, is the last guy who moved, okay? Except the last guy, right? You decide who is going to move next, okay? And what can be done, right? Depend on the history, right? So if the past, say you study the Ph.D, you can become professor, right? You don't study Ph.D, you become a professor, right? So it depends on what is accessible, the action, okay? It's depend on history, it's a set of the action, okay? Here, do note that we have the distinguished strategy and action, okay? Action is at any point of time what you can do, okay? And later we'll define what is strategy. So here we have to be very careful, this action, not strategy. Okay. In the previous case, action and strategy are the same thing. But in this world, action and strategy are different. Okay. Later we'll define what is strategy. Payoff will be only defined at the end. Okay. Only at the terminal, that will be the end. Okay. So this is a little bit, I would say it's very abstract. Okay. So let's actually define this in our match and pennies game, and then you will see how we can simplify this called game tree. Usually the game tree will do whatever we want to do. Okay. So here we have a N set, player 1 and 2. Okay. And all the history. History can be nothing have been started, your empty set. Okay. And at time 1, player 1 can choose head or tail. Okay. The history become nothing and head or nothing and tail, right? So that's this history. And time 2, okay, it's going to choose head or tail. So it's either head or head tail, tail head or tail tail. So the history can be like this. Okay, it's a terminal history because after that there's no more game. Okay, so the set of history is like this. Okay, there's a set of history. So why we need that? Because we need to make sure that we have to define carefully at different history who is going to move and what are possible things. Okay. So here at the beginning, player 1 move first. And the history of choosing head or tail by player 1, player 2 move next. Okay, the last time I know you don't need to calculate, right? You don't need to write. And what available at the beginning, player 1 can choose head or tail, right? And under head or tail, the same because player 2 can choose head or tail. Okay. And the payoff, right, is under HH. This is the payoff, and so on and so forth. Okay. So this is the complete description of the model. Okay. But never you use this one. What you're doing usually, you do this one. That is the usually you see, and this is complete description of what we have, right? Because we say in the graph, these are the payoffs. The solid dots are non-terminal nodes. These are terminal nodes. You start here the first history, first one move. These are the action. After each action, this player 2 move. Oh, can be 1 again, but this need not be 2. Okay, This just happened to be 2, can be 2 or 3 depend. And in this case, for the action. Okay, so this is the usually you will see in the textbook, right? But very often, sometimes you may not even see this. Okay, maybe some people will play a game and say 2-stage game. In the first stage, they play Connaught. Second stage, they play Bertrand. Okay, that is still a 2-stage game, right? Or the first stage game, they play rock, paper, and scissors. Second stage, they play matching pennies, right? Or the first stage is rock, paper, and scissors. If player 1 wins, then they play battle of sex. If player 2 wins, they play I don't know, prisoner dilemma. Oh, that's possible. Okay, then you can also, then they may not draw this one. Okay, they will verbally describe, but you can see the everything is there. Okay, and here this is called action, right? And here the strategy for player 2 have to say what is the action for every scenario. Okay, let me repeat. We end the class with the definition of strategy and action. Action is just telling you at the time he want to move, what is going to do. And the strategy have to say for every possible point he had to move, what is his action. Okay, but anyway, I think that would be okay. Okay, so we will talk about this in the next class, and turn out that you can do a Nash equilibrium here, but turn out that Nash equilibrium is not good enough. We'll talk about refinement. We call subgame perfect Nash equilibrium or subgame perfect equilibrium, and that will be our fundamental idea. Okay, so the main reason why this is not enough is because of people will not keep their promise. Okay, the idea is very often is before the guy got married, he usually promised the girl he would do A, B, C, D, E, F, G. Okay, after getting married, haha, bye bye, no longer following that, right? So you would think this is not going to be a good outcome, right? So you have to make sure that if this is a good promise, it must be that even you got married, this is going to be credible, right? He's going to follow through this. Okay, to analyze under this case, once we get there, it's still reasonable to keep that promise. Okay, that is application on firm entry, right? You will say, okay, new firm don't come in. If you come in, I flood the market, you can't make profit. Okay, but that is not credible because once you come in, you will not flood the market, because you flood the market with your product, then you also don't make any profit, right? So that is the issue. Okay, that's like don't come, I beat you. Don't come, I beat you. But when it's coming, you want to beat him. So that's the issue. But anyway, we'll talk about this next class. So have a nice weekend.